Welcome to my channel and thank you for watching the videos. In this video, question 4C of 1996 Calculus UPSC CSC Maths Optional Paper 1 show that the maximum and minimum of the radii vectors of the sections of the surface. This surface is given by the plane lambda x plus mu y plus mu z is equal to 0 are given by the equation this. So here we have to do maxima minima. We will be doing by two methods. First, let's we do with the help of Lagrange's multiplier method. Here we are applying method of undetermined Lagrange multipliers. We have two expressions given in the question. We take all the terms on one side and put them as phi 1, and second is planes equation. This we take and put all the terms on one side which are already there and put it as phi 2. This equation we have to obtain, we have to show. We have to maximize or minimize r square is equal to x square plus y square plus z square, means extreme values of this, and constraints are these two constraints. Method of undetermined Lagrange multipliers is for constraint problems. We will be doing by other method also, that is also same, but the procedure is little bit different. So del f upon del x, we differentiate. F is what? The term function r square, that is x square plus y square plus z square, for lambda 1 phi 1 and lambda 2 phi 2. If there is third constraint, we will add plus lambda 3 phi 3 and so on. So we differentiate this f with respect to x, y, z partially and put that 0. Because for maxima minima we have to write first derivative as 0. So when we differentiate f, it is 2x. There is no term here of x. So here we have lambda phi 1. In phi 1, first term when we differentiate 2x upon a square minus twice of r square into 2x, which gives 4x r square, because this is what? This is r square, plus lambda 2, and in this lambda is the term, into lambda is equal to 0. Del f upon del y, similarly 2y plus lambda 1 into 2y upon b square minus 4y r square plus lambda 2 mu. Here with respect to y, so mu is equal to 0. And in third it comes 2z plus lambda 1 2z c square minus 4z r square plus lambda 2 mu is equal to 0. So these three equations we got. Now we will find out lambda 1 and lambda 2 with the help of this. So we do some manipulation and get the values. When we try to solve this, we multiply first equation by x, second by y, third by z and add them. And whenever we apply undetermined Lagrange multipliers, then we add first term, then second term, then third term together in each equation. So first term from each equation when we are adding, it gives twice of r square. Then we are adding second term in all the equation. This gives 2 lambda 1 x square upon a square plus y square upon b square plus z square upon c square minus twice of r to the power 4. And third term gives plus lambda to this. And these two terms we solve with the help of two constraints, the two equations which have been given in the question. So lambda 2 is multiplied by 0 because it is 0. And from here we have now twice of r square plus twice of lambda into, from first equation it comes r to the power 4 because r square square, r to the power 4 minus twice of r4. Twice we can take in 0 means cancelled out, and then here it comes lambda 1 which is equal to 1 upon r square. So we got from here. Now from first, second and third equation we get x1. Once we got lambda 1, we can find out x1. So x1 has been written. Then further simplify it. Wherever x square plus y square plus z square is given, you can put r square there, and y and z. Once you put, you will get these. Now substituting x, y, z in the planes equation, the second constraint, and we get that r square is given by this, and in this r square is common, so we will divide it by that, and the term we are having this equation. As r square is not 0, means extreme values do exist and are roots of the given equation. Now we will think of second method. In that, we know that r square we have to maximize or minimize, so we differentiate that. So r square is equal to x square plus y square plus z square gives twice of r dr is equal to twice of x dx plus twice of y dy plus twice of z dz. I am not writing this. This is second method. Just keep writing if you want to do, because sometimes it helps. So as I said, r square is equal to x square plus y square plus z square. We have to maximize, minimize, differentiate it, which gives 2x dx plus 2y dy plus 2z dz. And for maxima minima, we have to put it as 0. So dr is equal to 0 gives x dx plus y dy plus dz into z is equal to 0. Now we differentiate the given equations, first constraint, and when we differentiate it, it gives twice x dx upon a square plus 2y upon b square dy plus 2z dz upon c square is equal to this was the right hand side. Now left hand side is r square whole square. So that is r to the power 4, which is 4r cube dr. Now for maxima minima, again we have to put dr is 0. So from here also we put dr is 0. It gives x upon a square dx plus y upon b square dy plus z upon c square dz is equal to 0. And third equation, the plane equation, also we differentiate. So that gives lambda dx plus mu dy plus nu z is equal to 0. Now the equations which we got by differentiating the constraints, given constraints, we multiply them by lambda 1 and lambda 2 and add them, and then equating to the coefficients of dx dy dz equal to 0. So this gives x, which comes from x dx plus y dy plus z dz. So x plus x upon a square. This comes x upon a square dx plus y upon b square dy plus z upon c square dz is equal to 0 into lambda 1, x upon a square into lambda 1. And from plane equation we get lambda into lambda 2 is equal to 0. When we write coefficient of dy 0, we get y plus y upon b square lambda 1 plus mu lambda 2 is equal to 0. When we put dz coefficient 0, we get z plus z upon c square lambda 1 plus nu lambda 2 is equal to 0. Now we multiply these three equations which we got after putting dx, coefficient of dx, coefficient of dy, coefficient of dz is equal to 0. We multiply by x, y, z respectively and add. It gives r square, first term, again first term we are adding. When we add all the second terms, it gives r to the power 4 lambda 1 plus 0 lambda 2 is equal to 0. So lambda 1 is minus 1 upon r square. Now we put this value of lambda 1 in the coefficient of dx, which we put 0, and we get x minus x upon a square into 1 upon r square plus lambda into lambda 2 is equal to 0. From here we get x is equal to a square r square lambda lambda 2 upon 1 minus a square r square. Similarly for y, for z we get the values, and r square is common, and lambda 2 is also common, so we divide it by that and we get the equation a square lambda square upon 1 minus a square r square plus b square mu square upon 1 minus b square r square plus c square mu square upon 1 minus c square r square is equal to 0. So this equation gives maximum and minimum values of r.